everyone, my name is Aimée Ogando and I am going to be presenting my Physics 2211 Lab 4. These are the objectives of this lab. The problem that this lab intends to answer is what data can we get out of examining the motion of a spring mass system oscillating. My hypothesis for this problem is that we can obtain information related to the change in position and change of energy in the system. The fundamental physical principle involved in this problem is Newton's second law. This law describes the behavior of objects for which all forces are imbalanced. It tells us that the net force of an object is equal to the mass times the acceleration, where the net force and acceleration are vectors. This ultimately translates to the change in momentum vector being equal to the net force vector times the change in time. Hooke's law states that the force needed to extend or compress a spring by some distance is proportional to that distance. As well, we will be dealing with the energy principle, which affirms that the work done by all forces acting on a particle equals the change in kinetic energy of the particle, meaning the total energy is equal to the change in kinetic energy plus the gravitational potential energy and the spring potential energy. These are the variables and materials used in this experiment. This is the procedure followed to do this lab. This is the video analyzed using tracker to examine the oscillating movement of the mass in its system for this lab. Highlighting the most important parts of the computational model, I first defined the mass of the object because it was already given in the instructions. Then extracted from tracker the initial position of the object, followed by inputting the value of gravity. Later, I calculated the spring constant with the formula K equals 4 pi squared times mass over period squared, and calculated the relaxed length with the formula LO equals magnitude of length minus mass times gravity over the spring constant. Then I defined the value of the change in position using the relaxed length and the stretched length. After that, I defined the formula to find the value of the kinetic, potential, gravitational, spring potential, and total energy of the system. Then I created a while loop to iteratively calculate this energy throughout the whole movement. I defined new variables for the initial energies at the beginning of the while loop and then calculated the net force as the sum of the gravitational force, calculated using mass times gravity, and the spring force, calculated using the constant times the length difference and the direction of the movement. Then I calculated the velocity and position of the mass using Newton's second law. Finally, I repeated the calculations for the change in position and energies of the system. This video shows a simulation of the predicted and observed motion of the oscillating mass created by the computational model, where the red circle is the observed motion and the blue circle is the predicted motion by the computational model. This graph shows the change in position in the x and y direction of the observed and predicted motion from the video and from the computational model. The discrepancies shown between both graphs and curves are caused by the source of error to be mentioned soon. A few interpretations taken from this lab are that all forces acting on an object are equivalent to energy that is equal to zero because of the law of reciprocity and the energy principle. All forces acting on this mass are countered to follow the laws of physics and the universe. We can use Newton's second law and the energy principle to analyze the change in position and change in energy in a system with oscillating mass. This lab may have some systematic and random errors like ignoring other interactions with the surroundings like drag force. Getting into the discussion of this lab, from this graph we can tell that the energy principle is satisfied because we can see that the change in energy is equal to the change in kinetic energy plus the change in potential gravitational energy, which equals zero. This proves no energy was created or destroyed during the entirety of the experiment. As well, we can see that throughout the graph, delta K cancels out delta U. Talking about the difference between the oscillation periods in the x and y direction, we can say that the oscillation period for the change in position in the x-axis is slightly greater than the oscillation period for the change in position in the y-axis because the movement is largely taking place in the horizontal axis. Also, since the lab didn't consider other forces acting on the system like drag, the differences shown in the graph may be largely caused by that. Thank you for your attention.